Hello, this is a presentation about metal air transistors for semiconductors free field emission air channel nanoelectronics. And your presenter is Lillian Hayden. This is the outline and its introduction, structure of the metal air transistors, how is fabricated a metal air transistor, transfer characteristics of the air channel transistors at the operating electric field and positive and negative bias, emission and conduction mechanisms, about the Fowler-Norheim and Stokes energy band gap analysis, and conclusions. Metal air transistors is a promising way forward for nanoelectronics in response to the limitation of silicon-based electronics. This technology simply takes a different pathway to the miniaturization of a transistor in an effort to uphold Moore's law for several more decades. The design of a metal air transistors solves a major flaw in traditional solid channel transistors. They are packed with atoms, which meant electrons passing through them collide, slow down, and waste energy as heat. Just imagine walking on a dense, crowded street in an effort to get from point A to B. The crowd slows your progress and drains your energy, creating a nanoscale gap between two metal points. And this gap is only a few tenths of nanometers, or 50,000 times smaller than the width of the human hair. But it's enough to fool electrons into thinking that they are traveling through a vacuum and recreate a virtual outer space for electrons within the nanoscale air gap. This presentation is about a technology where metal-based switchable nanoelectronics can be created on any dielectric surface with low energy requirements. A structure of a metal air transistor. Metal air transistor structure, you can appreciate it in these images that you have in front of you. These images of nanogap metal electrode. Devices consist of two implant symmetric metal electrodes, separated by nanogaps less than mean free path of electrons in air. That means it is less than 68 nanometers. The metal structure depicts drain and source configuration. A dielectric thin film offers separation from conductive backgate. If you see in the figure A, it's a top view of the optical image of fabricated device. On the image B, is a schematic illustration of the device structure with biasing scheme. Tungsten, gold, and platinum of 50 nanometers thickness were metals considered in this work. Dry thermal silicon dioxide as a dielectric was considered on a highly conductive silicon as backgate. So, as I was saying, in this presentation, we're going to compare the behavior of metal air transistors using three different materials, that is tungsten, gold, and platinum. How is fabricated a metal air transistor? Devices were fabricated with combination of electron beam lithography, thin film deposition, and photolithography. Substrates with thermally grown silicon dioxide on highly conductive silicon were cleaned by standard Purana method. For people who doesn't know what is a Purana method, it uses solutions that are a mixture of concentrated sulfuric acid with hydrogen peroxide, and they're used to remove trace amounts of organic residues such as photoresist from substrates. In this project, gate oxide thickness of 50 nanometers was utilized for gold and platinum devices. It was increased to 300 nanometers for tungsten to provide improved tolerance to the gate insulation. High-resolution electron beam resist polymethyl methacrylate was spin-coated on their pre-cleaned substrate. Spin coating was a two-step process to achieve a bilayer resist. First, EL3 collimator was spin coated and soft baked at 180 Celsius, grade Celsius, for 5 minutes. Then PMMA A2 was spin coated followed by identical soft baking. Resulting thickness of the bilayer resist was 120 nanometers. Next, a 10 nanometer thick conductive layer of chromium was deposited by an electron beam evaporation to avoid surface charging during electron beam lithography. To achieve maximum resolution, subsequently, exposed patterns were developed in methyl isobutyl ketone mixed with isopropanol in a 1:3 volume ratio. The samples now had nanogaps defined. On this structure, 50 nanometers thin metal film, tungsten, gold, or platinum for different sample sets were deposited. To aid addition of a 5 nanometer titanium layer was utilized. Both thin films were deposited sequentially by electron beam evaporation at high pressure in a Kurt J. Lester PVD-75 electron beam evaporation systems. Metal lift-off was performed in a hot acetone bath at 60 degrees Celsius with ultrasonication. Finally, photolithography was performed to create larger contact pads on nanoscale devices. Now we're going to talk about the transfer characteristics of the air channel transistors. The output and transfer characteristics of the air channel transistors are present on the figure in front of you. The output characteristics of point-to-point devices, that are the figures A, B, and C, are similar in positive and negative bias, with few noticeable differences. First, the operating electric field for stable emission is much higher for tungsten as compared to gold and platinum. This is due to lower melting point of gold and platinum, where electron emission from sharp tips causes localized heating and tips to rupture due to concentrated high electric field. Due to the localized melting tips become blunt and field emission degrades at lower electric field. However, tungsten with high melting point is observed to be stable at high electric fields of 150 millivolts per nanometer. The transfer characteristics of the air channel transistors in positive and negative bias are presented on figure D, F, G, and I, respectively. Devices turn off with increasing positive gate voltage in positive bias operation, as it is shown on figure D, E, F. This trend is same for all the three metals in positive bias operation. However, in negative bias operation, tungsten and gold-based devices turn on with increasing positive gate voltage, whereas it turns off in the case of platinum. This difference is mainly due to the tunneling mechanism that the respective metal air transistor experiences. Now we're going to talk about the emission and conduction mechanisms. But first, I would like to explain what is the Fowler-Nordheim and Stokes mechanisms. So the Fowler-Nordheim is a field emission is the process whereby electrons tunnel through a barrier in the presence of a high electric field. This quantum mechanical tunneling process is an important mechanism for thin barriers as those in metal semiconductor junctions on highly doped semiconductors. The Stokes is an effect or field enhancement thermionic emission is a phenomenon in condensed matter physics named after Walter H. Stuckey. In electron emission devices, especially electron guns, the thermionic electron emitter will be biased negatively relative to its surroundings. Carrier generation and transport mechanism for tungsten, gold, and platinum metal electrodes are presented on the figure in front of you. Dominant emission in tungsten and gold is due to the Fowler-Norheim tunneling, whereas it is thermionic or Stuckey emission for platinum. Now we're going to talk about energy band gap. On the figure that you have in front of you, the figure C, you can notice the linearity in current versus voltage, confirming the Stuckey emission in platinum. Tunneling distance is shorter in Fowler-Norheim, where electrons pass through the barrier at lower energy level due to the electric field as shown in the figure A. Whereas tunneling distance is longer in Stuckey, where electrons have to jump over the barrier to generate thermal energy, as is shown in figure B. This limits the number of electrons able to cross the barrier, as it requires higher amount of energy. Because of different tunneling mechanisms, we observe variation in the normalized peak currents for tungsten, gold, and platinum, air channel transistors, which is lowest for platinum. Energy band diagrams for platinum is shown in the figure B. Platinum has the highest work function among all the three metals considered in this work. In addition, electrode separation for platinum device is the largest. Because of these facts, it can be concluded that tunneling distance is larger and the work factor is smaller for platinum base. Furthermore, under the influence of gate voltage energy level, bends slightly downward by controlling barrier width, enabling few electrons to tunnel through a lower energy level as shown in the figure B. Therefore, we observe the Fowler-Norheim tunneling when the gate voltage is different from 0 for platinum. However, bending effect is not significant due to higher work function and electron gap, and hence the dominant mechanism remains to be Stuckey in all the cases for platinum. As the Stuckey emission is mainly due to thermal energy, the device turns on or off depending on the effective thermal energy generated with gate voltage. Conclusions. In summary, we present planar point-to-point structure of air channel transistors, fabricated using standard silicon technology. Metal electrodes based on tungsten, gold, and platinum are considered for this analysis. Separation between electrodes is achieved in the range of 11.5 to 36.1 nanometers, which is less than the mean free path of electrons in air, that is less than 68 nanometers. All three metal-based air channel transistors behave as transistors with significantly lower emission current of a few tenths of nanoamps. All devices behave as bidirectional transistors due to the symmetry source-drain geometry. However, variation in the positive and negative bias operation is observed depending on the tunneling mechanism of electrons. Experimental data shows that the Fowler-Norheim tunneling is dominant in tungsten and gold, whereas in Stuckey is only in platinum. Forward bias current is higher than the reverse bias current when the device experiences fault and Norrin tunneling, while it is of the same magnitude for stock emission under the influence of gate voltage. Further analysis with energy band diagrams show that tunneling mechanism of air channel transistors can be controlled by the effective field factor and the work function of the material. Most importantly, this work provides a platform for semiconductor-free, metal-based air channel transistors for future electronics, which has potential for low power and high performance applications on any base surface. Thank you very much.